Have you ever tried to write a string parser? If you're validating something simple like an integer, it's straightforward. But what happens when you have to handle signs, fractional parts, and scientific notation exponents all at once? A simple string like 0 or -123.456E789 is valid. But configurations like ABC, 1E dot, or a lonely period are completely invalid. Trying to write this using a massive web of nested if-else blocks quickly collapses into an unmaintainable mess of edge cases. To solve this reliably, we have to change how we think about parsing. Instead of looking at the whole string or trying to peek ahead, imagine a machine with a tiny, fixed memory. It reads the string character by character, from left to right, exactly once. It cannot look back. At every step, its current memory state tells it exactly what characters are legally allowed to arrive next. This elegant model is called a deterministic finite automaton, or a DFA. Let's look at the blueprint of this machine. We begin at state 0. If we see a sign, we transition to state 1. If we see a digit, we move to state 2. Notice that state 2 is an accepting state, indicated here as a valid destination if the string ends. If we see a decimal point from state 2, we transition to state 4, which handles fractions. If an exponent symbol appears, we move out to states 5, 6, and 8 to process the scientific power. Every single arrow represents an absolute rule. If a character arrives that doesn't have an arrow leaving our current state, the machine instantly rejects the string. No guesswork, no messy branching. The absolute beauty of a DFA is how seamlessly it maps to clean, highly predictable code. We don't write nested logic. Instead, we translate our state graph directly into a lookup table using a dictionary. We categorize each character into a type index, and then we simply update our current state by looking it up in our table. DFA of current state, char type. If the lookup fails, we return false immediately. When the loop finishes, we check if our final state is in our set of accepting states. This solution executes in strict linear time and constant space, guaranteeing maximum performance regardless of input size. Solving the valid number problem with a state machine completely changed how I look at data validation, and it opens up a massive, fascinating branch of computer science theory. If we want to dive deeper into how these abstract machines work and understand the mathematical laws that govern regular expressions, grammars, and computation itself, there is one definitive roadmap we should read. I highly recommend picking up Introduction to the Theory of Computation by Michael Sipser. Chapters 1 and 2 are the absolute gold standard for turning complex computation theory into clear, unforgettable intuition. Grab a copy, map out your own machines, and change the way you write logic forever.